Before I carry on to this video, I'll highly recommend you to know something. Alright, just to recap, is that this whole equation over here, which if you still remember, we're talking about u interpolate into x, and then from here over here we interpolate x into the c function. Alright, and these are all interpolation equations. Okay, if you were to go to the mind map itself, alright, this is talking about the displacement interpolations also. Alright, and then now we're going to talk about the geometry shape. The geometry shape is the ni. As you can see, are all these things, ni and ni. As you can see, the n's are different. For example, if you're talking about the u to the x, alright, you're talking about x2 minus x1 and things like that. Alright, if you're talking about the x to c, alright, the c domain, the shape functions is something different already. Okay, so as you can see, the shape functions is totally different from each of the case. However, the geometry shape itself, to my extent, is that this is node 1, this is n1. Okay, so if you still remember back in the old videos, if you never, then it's okay. This is the n1, this is the shape function. So this tells you the shape of the function itself, some triangular. Alright, and node 2 and node 1. So at node 1, the shape function n1 at node 1 is 1, somewhat the unique vector, you would say. Okay. However, you have n2, you're talking about this at node 2 it is 1. Okay, so this tells us that there will be a displacement at node 1, and this tells you there will be a displacement at node 2. That's just the meaning of that. Alright, so therefore, as you can see, is the shape function n1 at node 1 is equals to 1. Alright, the shape function n1 at node 1 x1 is equals to 1, and then the shape function at x2, or node 2 is equals to 0, as you can see. And therefore, from here you can see that the shape function of n1 at node 2 or x2 is equals to 0. Alright, so if you were to have n1, alright, where it's x1 plus n1 x2, you always have equals to 1, because it's always, this thing is 1, because this thing will become 0. Okay, but please do not confuse this thing with this thing over here. Alright, this thing has no value at all. This thing becomes a vector now. Alright, because they're in different directions. n1 and x1 tells you this one. Okay, because it's the shape function at the node 1 is there's a displacement over here. n2 and x2 tells you that you're talking about this shape functions at x2, which is a different case. So if you add up together, although they are in the same direction, as you can see, they are going up, but they are at a different somewhat basis or different functions. n1 is this one, n2 is this one. So if you add them up together, you'll give you a certain other shapes. Alright, so that's why I want to convey to you that this is something that pretty intuitive. Alright, you may need to understand. And I may be wrong over here, this because I feel that something is wrong, because I copy in the notes is n1 plus n2 is equals to 1. That's what he said. Alright, and then if n2 is 0, then n1 is equals to 1. If n1 is equals to 0, n2 is equals to 1. But however, this may not be the case, because we are talking about if n1 at node 1 and n2 at node 1, then you're talking about that. If it's n1 at node 2 and n2 at node 2, then it can be also equals to 1. Alright, but however, if it's at n1 at node 1, n2 at node 2, then this shouldn't be 1 anymore. This should be some form of a vectors already, telling you there's a displacement. Alright, if you don't understand what I mean, is that if you have an n1 over here, there is a node 1 and node 2. Right? So if n1 at node 1 it is 1, at n2 at node 2, at node 1, this will be 0. So 0 plus 1 is 1, right? Alright, repeat again. So if n1 and node 1 it is equals to 1, correct? So therefore this one becomes 1. Alright, this one will become 1. At n2 and node 1 this is actually equals to 0. So n plus 1 plus 0 is equals to 1. So if let's say your node, if you're looking your shape functions at the same node or at the same point, alright, you'll always be equals to 1. Okay, it's because as you can see at f1 is this one, at n2 is 0. And then if it's at node 2 now, if I simply change this as node 2 and this is node 2, alright, then you're talking about this thing as 0, n1 as 0, and then over here n2 node 2 is 1, so therefore it equals to 1. Alright, but please do not be confused with, let's say, n1 and node 1 plus n2 and node 2. Then you're talking about vectors already. And this is a very powerful understanding you need to know, because yeah, so do not be confused by the points. Alright, be very careful of the node they're talking about. Alright, if it's n1 and node 1, then it's this one, n2 and node 2 is this one. Alright, then you have not equals to 1. If it's n1 and node 1 and n2 and node 1, or n1 and node 2 and n1 and n2 and node 2, then as you can see, if they are the same number over here, this means that they're definitely equals to 1. Alright, if there is different number over here, like as you can see, this is 1, this is 2, then definitely this will not be 1. This is some other stuff already. This is totally a vector. Okay, so be in like 2, so this will be a vector to some extent. And so far I've been talking about this shape function over here, right? We say that if it's at n1 and node 1, then it will be a spike of 1 over here. Alright, this is for this case, which if I were to draw it in a thicker line, is this one. Alright, so this is for the u displacement lah. For the x to the c displacement, it's the same thing. The explanation is the same. Alright, at n1 at node 1, alright, you have a spike over here again. Okay, and then at n1 and node 2, then you're gonna have another spike over here. So n2 and node 2. Okay, and wait they actually say that n1, alright, at n1, this is n1, at c1, which is this one over here, is equals to 1. So at this point it will grow up. And then at n2, if I were to switch it up again, alright, at n2, this is n2, at c2, which is this one over here, your c2, you have a spike over here equals to 1. Okay, so this is the same thing, just be mindful of the thing that is happening over here. Okay, so this is something that you may need to understand. And now if you happen that you may if you still remember this thing over here, this b, alright, when you sub in if you still remember the very first part of the derivation of the weak form, alright, this b is your strain displacement matrix. Alright, and therefore this strain displacement matrix is dn. Your shape function, the change of a shape function is against your dx, the changes of your shape function. Alright, your shape will change across a certain dx. Or maybe you have this dx over here across a huge, and then at least you get what I mean, it's just some changes across dx, that's all. Alright, and we can rewrite this thing in terms of a chain rule type of concept. So this chain rule type of concept is something like d psi dc, alright, over dx multiplied by dn over dc. Okay, and therefore if I were to bring this over here, alright, this whole equation over here somewhat links your shape function of the 1 minus c, alright, with the shape function of in terms of the x. This is in terms of the x, this is in terms of the c. Alright, so this equation over here is trying to link this thing to this thing. Alright, by taking that this dc over dx multiplied by dn over dc, you cancel, you have dn over dx, alright, which is your strain displacement matrix. So in order to do that, this chain rule tells us that this whole thing over here is we call the J, your Jacobian Jacobian stuff. Alright, and the Jacobian formula is half multiplied by x2 minus x1. Alright, is equals to j, or is equals to this dc over dx. Okay, j is equals to this one. As you can see, this thing over here is actually very similar to your shape function of this thing. Alright, so from here, as you can see, that 1 minus c is actually x2 minus x1. Okay, I should say that this thing over here is talking about is somewhat the same thing of this. Alright, because this half times 1 minus c is talking about half of the beam, if you still remember. Thinking about this half of the beam. So we're talking about only one piece of it. Alright, or you can just simply say that x2 minus x1, okay, if you go all the way to the interpolation, alright, x2 minus x1 is simply this length over here. Half of this length will be the half of this bar, and then this bar over here, if you still remember, this whole bar will be translated into this thing over here, your from your L to your lambda. Alright, so this being over here, if it's half, is somewhat talking about this thing over here, which is half of this also. So there's some relationship between here, and then I just want to show you. Alright, I think this is somewhat confusing, but at least you get to see that what is actually the meaning of the Jacobian. It's just taking half of the bar itself, and then you differentiate by its dx to see how does it change across this portion. Alright, how does it change across this portion for n1, and how does this change this in this portion for n2. Okay, but they are just generalizing things in a way. Alright, so still I may be wrong, but at least this shows something about that. So if that's the case, then I know that my j is equals to dc over dx. So I'm gonna differentiate in terms of